Okay, so I've sent everyone, for those of you who everyone's turned in homework to, I've sent those back with wherever you lost points. So what I did with the grading for homework 2 is, all right, so the average turned out to be, I think it's about roughly 94, somewhere in that range, like somewhere in the low 90s. What I did with is I curved by 18 points. Now it seems like an odd amount. I chose that amount because effectively what it means is it made the had the effect of making the section 2.4 exercises equal to a bonus. And then the let's see, the highest, therefore, it was possible to get scores of over 100. The highest was a 113 out of 100. Okay. So you have any questions? Like I said, if any work accidentally got overlooked, because of course everybody is sending lots of files, and then there's a lot of exercises to sift through. So if I miss anything, let me know. Okay. And I want to emphasize, do not take this as an indication that I will for sure do the same thing with homework 3. So one of the reasons I implemented curve was that I was concerned about possible confusion about what the scope of the assignment was, because we have these explorations throughout the chapter, which was the only thing that you guys had on homework 1. But then also this assignment had also this batch of exercises at the end of a chapter. But and this won't apply for homework 4 because we're running out of time. But so here in homework 3 we have regular explorations, same like before, section 6.1.6.5, and then exercise at the end of a chapter. So I'm going to be looking for these. You'd better do them. So these 6 that I've picked out, and I've accounted for that in the suggested timelines for finishing these. Okay. So don't back onto the generous curve next time. Okay. Now, so as far as where things stand right now, so last time looking at numerical differentiation based on either a Taylor series expansion, or Lagrange interpolation to represent derivatives in terms of function values. And I kind of goofed when I misremembered what the schedule said. I actually thought for a while there that I was going to be starting integration today, but I'm not. So I will certainly have time for any questions you guys have on anything, but any remaining time is further illustration of developing differentiation rules, numerical differentiation rules, not as opposed to the analytical ones you learned in calculus, and including error analysis, so which will help with some of the problems. Also using MATLAB for assistance in deriving these rules. Okay, so starting on Thursday, same idea, but for integration. meaning that the approximate integral of f, and I should emphasize here, this is a definite integral. So in fact, all the integration techniques you learned in Cal 2, we will use almost none of them. The one we really care about is the power rule, because that's for polynomials. So the approximate definite integral f of x is the exact integral of a polynomial that approximates f of x. So we're already using that idea, and that'll be reinforced today with derivatives. Same idea for integrals. So we approximate f by polynomial. Today, it's about, and also last time, it's about differentiating it and plugging in x naught. What we'll do next time is take that same polynomial, integrate it over some interval ab. So by the end of the semester, we'll have a number of different approaches for approximating derivatives and integrals, and which will be very useful to us for solving other problems numerically, like differential equations, etc. Okay. Now, I am extremely surprised that, having put out the 3/4 term take-home test nearly 72 hours ago, well, I guess it's, okay, more like 60 hours ago, that no one's had a single question about it. Is anybody diving into it? Or you took one look at it and you're like, The question is similar to the homework, so... Okay. Oh, all right. Well, there's no... okay, so you already have a similar question on the homework? Or okay, well, I'll make time for that too. But, and certainly, I mean, you guys are allowed to ask questions on it just like with anything else. Certainly, if there's any questions related to what is the problem asking, I want to make sure there's, and I know that only some of you are doing it, and like I said, maybe some of you took one look at it and you're like, nah, I'll take my chances of a homework. So, you know, we'll see who turns it in. Okay, so does anyone have any questions on that? Or if not that, on the homework? Okay.
So for exploration, 6.4.2.
Okay. Hold on. We'll have there. Oh, by the way, the notes I typed up for last class, based on some questions, I've gone back and updated those. Like that's related to 6.1.4. So if you're still working on that one, you might want to take a look at that. Okay, so 6.4. Okay. All right, let's get that one up here. Where'd it go? Ah, okay, yeah.
On the similar problem that you had whenever with us in the notes.
Yeah. This one right here.
You had the xi. I guess that's how you still say that. You had a restriction on that from 0 to 1. So I was going to know if that still applied to 6.4.2.
Oh, yes, it does. So in general, the unknown point, xi or xi, or I never know how to pronounce my Greek letters. It lies in an interval containing all of the interpolation points x naught to xn. So, in this problem, the interpolation points are between 0 and 1. So yes, xi is in between 0 and 1. Okay.
Next question is also in 6.4.
Number 4. Okay. The induction one. Okay.
So when we start with the induction, do we use the original definition, the tk of x equals cosine, etc., whenever we start with the case of k equals 1?
Yeah. So, so use the definition for base case. Yeah, to verify that you get the right coefficient for that.
To move on to the tk plus 1, we use the other definition that was given.
The recurrence relation.
The recurrence.
Yeah. Okay. Okay. I know I probably shouldn't say this on video, but whatever. I'm not as picky about grading proofs as some of my colleagues, but I'm looking for essential ideas. Is there a base case? Is there an induction step? So, I mean, the general principles, but okay.
And then my last question was for exploration 6.5.
Okay. 6.5. Okay. 6.5.1.
Correct.
Okay.
Just to confirm that, like, the first step would be to create a divided difference table.
Yes, it would. Yeah, and actually, I did an example similar to this, where it wasn't the Hermite case, but where you just have some sort of derivative information. Yeah. Okay, so. Okay. One thing I've noticed is that since I put comments in here based on whatever section I happen to be talking about, like these problems from 6.4, 6.5, I'll be like the next day or two, I'll be going through all these notes that I've posted on the site, and I'll be because right now they're organized by date on which I gave these hints, but I'll organize these like by section. I'll post them somewhere, like somewhere in the site. So when you're working on problems in a particular section, you don't have to be combing through several of these documents to find the hint that might actually help you. Okay. Okay. Does anyone else have any questions either on the yes?
Okay, it's 6.4.1 and 2. I'm not sure how to relate the left-hand side to the right-hand side. I can prove the right-hand side, but I can't figure out how to relate them.
Okay. 6.4.1. So, okay, so left and right side of this.
Yeah, like I can prove the right side and why the right side works, but I can't prove how it relates.
Okay. So in other words, like you have something else on the left side, or?
Well, no, it's like I'm just it's a misunderstanding of what we're supposed to be doing. It says prove it, and I can prove that the right side, the n plus 1, that I can prove that that works because of Pn, and because of how Pn works. I can't figure out how it relates to the whole left side, fx minus Pnx.
Okay. All right. Yeah. I'm trying to figure out what to do with what you. Okay. Because when you say that something works, in other words, you're seeing where the individual pieces come from, or.
Yeah, like I know that because f is n plus 1 times continuously differentiable.
Yeah.
That because we have theorem 6.3.3 says it's differentiable for n times.
Yeah.
N plus 1 is just another integer. That's where we get fn plus 1 instead of just fn.
Right.
So we get n plus 1 exclamation. It was just n at the beginning. I don't know. I know that we get the capital pi from the explanation back on page 193 about p of n. Don't know where f of x and minus p of n gives us that whole thing.
Okay. All right. Okay, so you're seeing where certain pieces come
I'm
from.
knowing where the pieces come from, but I don't know where it all.
Okay.
all comes together.
Here's what I'm going to do. Okay. Have you made use of the first hint?
Yes.
Okay.
I don't think I did that right.
Okay. And I don't remember if I brought this up before, but in case, well, regardless, it's worth repeating now, even if I did. Okay. So, all right. I'm gonna try to give a framework that hopefully, where you can hopefully take all these pieces that you're seeing and put them together. Okay. Dang it. Okay, look, I paid $126 for you, so not be putting these extraneous characters. All right, so I'm going to define n plus 1, and it's Pn that we want the error in. But Pn plus 1 be a polynomial that interpolates f at the same points, but we throw in one more, x. So we have a grand total of n plus 2 points that we're interpolating at. So therefore, that's why the degree must be n plus 1. Now, so I'm going to give a hint. Newton form is what we want to use here. So if we express Pn plus 1 in Newton form. Now, here's, okay, so now a little bit tidbit I need from you guys, because all of you, or most of you, entered this on the Canvas quiz that dealt with Newton interpolation. This was section 6.3. What is so nice about Newton interpolation compared to any other approach? What's its advantage? Exactly. So if you have a interpolating polynomial of a certain degree, and you want to add a point, which is what I'm doing here. You have a point, you're interpolating points x0 up to xn, we're throwing in one more. Then you can express the new polynomial in terms of the old. So what you can say is Pn plus 1 x is equal to Pn of x plus the next term in the Newton form. Okay, so now, what does the next? Now, as far as the next term in Newton form, this is where I want you guys to pick up from here. And if we look at, but I'll show you or remind you of Newton form in general. Okay, well, here's Newton form in general. This is on page 223. Yeah, unfortunately, I guess giving page numbers in the book is kind of a dicey proposition because I've been staying up till 3 in the morning pretty much every night working on this book and working on earlier chapters, and that's changing of page numbers. Okay, so here's the general Newton form. So what's happening is Pn plus 1 is equal to Pn plus the next term, which looks like this. There's a divided difference. There's some linear factors, and you have to keep in mind what is the divided difference. Okay, so the next term, divided difference, product of linear factors. but for degree n plus 1, rather than degree n, like we have here. So keep that in mind. And no, this exclamation point is not to do a factorial. Not here anyway. Okay. Now, for the divided difference, that's where the other part of the hint comes in. So I think the next thing to keep in mind, so the last tidbit I'll give you for this problem is, what do we know about, what else do we know about Pn plus 1? It agrees with F, at all of the interpolation points that we are using for Pn plus 1, x0 to xn. And x. So the idea is, if you have a interpolating polynomial that you know interpolates a certain function at certain points, then at those certain points, the two are interchangeable. So really, this Pn, the introduction of Pn plus 1, I mean, it's the error in Pn that you want, but admittedly, the introduction of Pn plus 1 is a little bit of trickery to give you all the pieces you need in the in this error formula. So here's your framework. See if you can use this framework to get all the pieces of this error formula to fall into place. Okay, do we have any other? Oh, you also had 642, is that?
Yeah, it's just trying to figure out where the E of x is coming from.
Okay, so what you're doing is, all right, so it's going to follow the framework of this example, where, okay, so as far as where it's coming from, because, so this is part of your given information as a function that you're actually fitting. So I guess I'm not sure if I'm getting it. Sorry, what?
I have an unupdated version of the book.
Oh. Okay. All right. Okay. Any other? I'm not. So, is anybody doing a take home? Okay. What? Okay, that's something. Okay. All right. I mean, I don't really care. I mean, I'm grading something for you no matter what. And actually grading this on top of the homeworks that are already there is not a big deal because there's only 5 problems. Okay. Because what I found was it seemed like almost half the class was interested before. So, okay. All right. And we have let's see, 8. Well, there's another roughly 56 hours until it's due. So I know how last minute you all like to be. Okay. So our homework problems, nothing else there either. Okay. Everything's peachy, or as much as can be hoped for. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 10, 16. Oh, I'm missing somebody. Okay. All right, so I'm going to show you first a code snippet that it's actually the solution of an exploration that I did not assign, but it happens to be useful for one that I did assign. And I figure any code samples are going to be helpful for various things anyway, just to get your fundamentals down. So what this function does, make Lagrange, you're giving it a vector of x values, like your x naught up to xn. So there's going to be n plus 1 values in this vector x. And what it does is it creates the Lagrange polynomials for these points, and it returns their coefficients in this matrix L. So now remember, polynomials are represented in MATLAB as row vectors of coefficients. So each row of this matrix is going to have the coefficients of a Lagrange polynomial. So how I make these Lagrange polynomials in this function, so first I need to know how many points do I have. So now really, in terms of a notation I've used elsewhere, this would really be n plus 1, but we're just going to call it n, because for the sake of a function, it'll work. And then I want to, x, I'm not assuming that x is a row vector or a column vector, I just know it's a vector. But for what I'm going to do next, I want to force it to be a row vector. So what I'm doing here is I'm using a reshape function. So a reshape function can be used to reshape any vector or matrix into some other form, different number of rows and columns, as long as the number of elements, the total number of elements, has to stay the same. So I make this, I force this x to have one row, that's the second argument, and then n columns. So now I know that this is a row vector. And then I make a matrix, a zero matrix, where I'm going to store the coefficients of Lagrange polynomials. So the space is there to put these things. And then I make an identity matrix. Now the reason why I want an identity matrix is, what do we know about the Lagrange polynomials? What values do they have at the given interpolation points? 1 or 0. And also, more specifically, there's 0 at all of the points except one of them, where it's equal to 1. Well, that's what the identity matrix is like. The identity matrix, so if I make a 5 by 5 identity matrix, for instance, each row has all zeros except for one of them is equal to 1, and the ones are going down a diagonal. Okay, so the identity matrix gives me the y values I need for my Lagrange polynomials, and I have the x values. So now I can just go in a loop. In the loop, I just call polyfit. So I'm letting MATLAB's built-in function do the heavy lifting here. So I pass my x values, and here I select one row, row j, of identity. So that would be the y values for this particular Lagrange polynomial. And then the degree should be one less than the number of interpolation points you have, as usual. So polyfit requires that. So then p comes out, and those are the coefficients of this Lagrange polynomial. And then I store that in my matrix, and I just do this in a loop, and I'm done. Okay. So to illustrate the use of this function, I'm going to go back to an example. All right, so here I had an example where my x values are -1, 0, 1, and 2. And I'm using this example because I already have Lagrange polynomials on hand for it. So for checking. So I'm going to make a vector of x's with these x values. So x is, well, I could do this, -1:2, just because it's the integers are consecutive. But more generally, if they were not equally spaced, I could do like -1, 0, 1, and 2. Okay, so those are my x values. And now what I'll do is call my make Lagrange function. And I'll have it print out the matrix L. Actually, I'm going to do format short on this. I don't need to see 15 decimal places. Okay. So here are my coefficients of my Lagrange polynomials. Now let's interpret this. First row is using a notation from a book, L free 0 of x, and it's equal to 0 at it's equal to 1 at -1 and equal to 0 at the other points, 0, 1, and 2. And if I read off the coefficients here, so I have -1/6, 1/2, and -1/3. So it's equal to -1/6. So if I factor out a -1/6 from all this, I'll have x cubed minus, so 1/2, so that's 3/6, so 3x squared minus, plus 3x squared minus 2x. Okay, so that's the polynomial that is being displayed here. So if you worked out the coefficients, -1/6. Oh, hold on, I goofed. Yeah, I already factored out a negative number, so that should be a minus, and this should be a plus. Okay, so -1/6, 1/2, and then -1/3. So then, if I compare that to what's in the book for that example that uses the same interpolation points, okay, and thankfully it's right, -1/6, x cubed minus 3x squared plus 2x. And then we have the other Lagrange polynomials down here. So like x cubed over 2 minus x squared minus x over 2 plus 1. And sure enough, we can see those coefficients in the second row, and so on. So any situation where you need all of Lagrange polynomials, which is convenient for forming numerical differentiation or integration rules, you can, then this function will give them to you. So when you get to the problems on numerical differentiation, this is the start of homework 4, so 815, this will be helpful. So I'm going to post this on the site after class. Okay. Now, so what I'm going to do is I'm going to step through the derivation of one of the numerical differentiation rules using both approaches, because you have to use both approaches on that homework, Taylor expansion or Lagrange interpolation. So the rule that I'm going to use is one that's already presented. Okay. This one right here. So this is the center difference. So f prime is approximated by the center difference, where we use a value of f at x naught plus h and x naught minus h. And then we have this error term that's proportional to h squared. Oh, I just realized I totally forgot something. Okay. I'm going to divert for a second and come back to this. There's some comments I wanted to make based on what I saw with homework 2. Okay. Whoops. Didn't want to delete everything. Okay. Yeah, just based on what I saw in what I graded. So these are some things that you want to be aware of, because they're not necessarily things I took points off for this time, but it could affect you down the road. Okay. This problem, getting the condition number of cosine x is pi over 4. Most people got that correct, what the condition number is, but then at what value could it be particularly large? Well, the condition number, relative condition number, is given by this formula here, xf prime over f. Well, if f can be 0, then you got a problem. That condition number can be infinitely large. So for instance, when cosine is equal to 0, at like odd multiples of pi over 2, then you have something very ill conditioned. So at the given value x naught, at pi over 4, it wasn't a problem, but at those points it could be. So you might want to use the absolute condition number instead, where you don't have this, this division. So that's one thing I noticed that people were missing. The one where you're measuring convergence of cosine, right here, no, not cosine, this one, of exponential. So you fill in your Taylor series for your exponential, you cancel what you can. And what I saw in some cases were people correctly getting that the difference between your function and the limit, which is 1, is something that's order h cubed. It's something times h cubed. But then still gave a different response for like what's the actual convergence rate. Like saying order h or order h squared. So after you do your simplification, whatever you get as your leading term, that's the answer. That's the convergence rate, order h cubed. Because what happened was these other terms of lesser powers of h, they all canceled. So it was almost a situation of, I just made a judgment call not to take off points because you did the Taylor series manipulation correctly. But it was almost a case of snatching defeat from the jaws of victory. Okay, so so it's the lowest power of h you get after you simplify as much as you can, not before. In floating point arithmetic, and dealing with like this product of like 100 pi times 10e, and 5-digit arithmetic, I saw a lot of chopping instead of rounding. So you really should round to nearest, otherwise it would throw off the results. Okay, and certainly rounding is more accurate than chopping, so you want to make sure to do that. Okay. Yeah, one thing that was strange in the next one, where you're working with, you're following this example to get the binary digits of pi up to a point. So I saw like the correct exponent being gotten, the exponent is 1, and then the correct digits in the mantissa, you know, something along these lines. But then writing down that the exponent was 12. 12 is the amount of precision you have. The exponent is when you take the logarithm number to your base, which in this case was 1. So I'm not sure where that was coming from. Okay. And then, yeah, and the mantissa should be expressed in binary, bless you, just like in this example. But not as many digits. Okay. Lot missed on this one, 224. Largest and smallest positive numbers. Emphasize positives. In other words, 0 is not allowed. But to get the smallest number, you want the smallest possible exponent, which is minus 20, but you also want the smallest possible mantissa. The smallest mantissa is this. All digits set to 0 except for the least significant digit, which is set to 1. So your smallest mantissa is 10 to the minus 4. Your smallest exponent is minus 20. So the smallest positive number is decimal, so 10 to the minus 24, not minus 20. In a later problem, 227, where you're required to assume normalizing, then the smallest mantissa is 1, and then your smallest number is 10 to the minus 20. The next one, getting value of overflow for this kind of floating point system, this was not actually a MATLAB problem. This was working out on paper using a formula. And most did, or actually, I think just about everyone did this correctly, but then you might have tried it in MATLAB and got inf, and then saying that it was in infinity. But since you wrote down the correct expression, I didn't take off points. But it's not infinity. So now this would not work in MATLAB because in IEEE, the largest allowed exponent is 1022, not 1023. So you were never going to be able to enter this value into MATLAB anyway, but the problem wasn't asking you to. So it is an actual number. Okay, certainly these problems, this pair of problems cause a lot of headaches, 12 and 13. Dealing with these sums. Now, a number of people got number 12. What you do is you basically, the answer to both of these is actually equivalent. You factor out the largest one in the whole bunch that you're adding. So here, you assume x is greater than y. You factor out an x. And then what you're squaring after that is a magnitude less than or equal to 1. So then you don't have to worry about overflow. In number 13, you actually do the exact same thing. Whichever is the largest of all these n numbers, factor it out of the sum. And then everything you're squaring in here in your sum of squares, again, magnitude less than or equal to 1, so you don't have overflow. That's why I was tying the two together, that the way you handle them is actually the same. I saw a number of very elaborate approaches for number 13, but they would also have their issues. Okay. Number 18. Yeah, this one right here. A lot of people delivered the correct modification. Now, the thing is, when we're dealing with computer arithmetic issues, we're dealing with situations where we would be able to evaluate this, no problem, if it was exact arithmetic, but when you do it on a computer, then you have a problem. For instance, a lot of people looked at the case where x is equal to 1 or minus 1. When x is plus or minus 1, there is no hope in exact arithmetic or computer arithmetic. The expression is just undefined. So, from a numerical point of view, it's not even something you look at. You want to look at situations where in exact arithmetic it's okay, but because of the unique issues with computer arithmetic, not being able to represent certain numbers due to overflow or underflow, or really overflow is what we care about, or catastrophic cancellation, that's where you want to check. So the problem here that could be fixed is when x is nearly 0, because then both of these are roughly equal to 1, and you have this subtraction in between, just this one, that causes catastrophic cancellation. So then the way that you all chose to rewrite the expression, where you get like 2x over 1 minus x squared, that solves the problem. So you delivered the correct solution, but you didn't necessarily identify the problem that was being addressed. Because after you rewrite it that way, there's still no hope at x equal plus or minus 1, but at x equals 0, you're good. Or you're particularly small x, because then there's still subtraction, but there's not a risky subtraction. And finally, okay, in exercise 5, okay, taking your new quadratic formula and using it, this function requires an if statement, because which quadratic formula you use for which root depends on the sign of b, whether it's positive or negative, because then it determines which case you're doing a risky subtraction and you have to avoid. So for some people who had the two quadratic formulas, but they weren't applied properly. Okay, so I just want to point those out. These are common things that I saw in homework 2, whether I took points off on them or not, that I wanted to make you aware of. All right. So what I was about to do with numerical differentiation, standard difference, and we'll see how much time I have for this today. So the standard difference is plus h minus fx naught minus h all over 2h, and the error term is order h squared. Okay, so how this is derived using either Taylor expansion or Lagrange interpolation. Okay, and one thing I want to point out, because it happened to be right in front of me in what I was looking at in the book when I was citing standard difference. Okay, from here. This example below is good for showing why we have numerical differentiation instead of having computers do differentiation the way we do by hand. Because here's your function, pretty ugly function as it is. Look how ugly the derivative is because of all the rules you're using. Product rule, quotient rule, chain rule, and so on. I just made up this function up just to have a nasty example. And how much work it would take to evaluate this at any particular point, when you can evaluate this much simpler expression at just a couple points and then get a very accurate approximation of a derivative, which I do here. So here I just pick a couple points, and I have an h that's not even all that small, and I get something that's accurate to within like the 4 decimal places. And for my purposes, that could very well be all I need. A lot of applications, real-world applications, you only need to be in the ballpark anyway. Sometimes just like 1% error is very acceptable because there's so much uncertainty in what you're modeling anyway. Okay. So that's just to give you some reason to appreciate why we have these rules instead of, because you can write software. People have written software that does differentiation like we do. It's just not that practical. Okay, so the form of the approximation that I'm going to use in both approaches is f prime is equal to, I'll have a 1 over h outside, and then in the square brackets, I'm going to have, I'm going to use x naught minus h, f of x naught, and f of x naught plus h. And notice the way I'm indexing the coefficients. I'm using multiples of h, minus 1, 0, and 1. So I index the coefficients the same way, minus 1, 0, and 1. It's a little unusual, but at least it helps me keep things consistent. So now what I do is I'm going to just keep morphing this in several steps. So what So what I'm going to do is any point other than x naught where I'm evaluating f at, so x naught minus h, x naught plus h, I'm going to replace with its Taylor expansion. Okay, so I'm going to do a lot of copy and paste here. All right, so f of x naught minus h, I'm going to fill in is Taylor expansion. So I have f of x naught minus h f prime x naught plus 1/2 h squared f double prime x naught. And I'll go out one more term. Minus 1/6 h cubed f triple prime x naught. And then I'm going to do dot 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 after that, because anything after this is order h to the fourth. It's going to end up not playing a role. I mean, basically, if you're not sure, you can always go out too far and then trim back on whatever terms you actually use. So that's my expansion for f of x naught minus h, and now I want to do the same thing for f of x naught plus h. So I'm going to just copy this one, and I have to change the signs. Now, this expression is too long, so I need to fix that. Okay. Okay. So in my expansion of f of x naught plus h, I need to change my minuses to pluses. Plus, and then plus. Okay, so all I've done to go from here, first step to second step, I've replaced f of x naught plus or minus h with their Taylor expansions. Now what I'm going to do is I'm going to collect terms according to, I'm going to group f of x naught terms together. I'm going to group f prime terms together, f double prime. So I'm going to combine it by that, because right now we're grouped by coefficient, which is not really helping me. Okay, so that's going to give me is, if I group all of the f of x naught terms together, I have one here, and here. So I'm going to have c minus 1 plus c naught plus c1, all times f of x naught. Okay, now I'm going to look for f prime of x naught terms. Well, I have one here and one here. So that will give me plus minus c minus 1 plus c1 h f prime of x naught. And f prime of x naught is what I'm looking for, because that's what I have on the left side. Then I want f double prime terms. I have one here and here. So that's going to give me c minus 1 plus c1, 1/2 h squared f double prime. Okay. And then I also have f triple prime terms. Okay, so that's going to be, okay, c minus 1, oh, actually minus c minus 1 plus c1, 1/6 h cubed f triple prime plus dot dot dot. Okay, and unfortunately, again, this expression is too long. So let me fix that real quick. Okay. All right. Oh, and let's not forget plus error, which we'll deal with at the end. So now I need to make this expression collapse as much as possible to f prime. So what does this give me? A system of equations. Okay, so this term, f of x naught, I want it to go away. So I'll have c minus 1 plus c0 plus c1 equals 0. In general numerical differentiation, all the coefficients must sum to 0. Second equation here, minus c minus 1 plus c1. I want these to equal 1 because here I have an h. Outside, I have a 1 over h. Those are going to cancel. So if these sum to 1, then I have f prime by itself, which is what I want, because it's all I have on the left side. So I have c minus 1, or minus that, plus c1 is equal to 1. Okay. And then here I have an f double prime term. I want that to be gone. So, whoops, I need to fix that. Okay, that should be a minus 1. So these two coefficients, c minus 1 and c1, they must sum to 0. So okay, so this is my system of equations that has to be satisfied. Now, this is something that you would not have any difficulty solving by hand, but for the sake of explorations coming up in homework 4, I'm going to have MATLAB do it for me anyway. So my my matrix is going to be all right, so my first equation, all the coefficients of my unknowns are 1. So I'll fill that in the first row. Second row, coefficient of c sub minus 1 is minus 1. There's no c0, so that has a coefficient of 0. And then I have a c1 by itself, so that gives me a 1. Third row, coefficient of c minus 1 is equal to 1. There's no c0, so that gets a 0. And then I have a c1 by itself. So those are my coefficients of this linear system that I have right here. And then I have the right side. 1, 0, 1, 0. So now my coefficients of my numerical differentiation scheme, A backslash B, A inverse B. So I'm solving a system of linear equations. And I get minus 1/2 for c sub minus 1, 0, so f of x naught is not involved at all, and then 1/2 for c1. So if I fill that in here, okay. So now my approximation, well, actually what I'm going to do is I'm going to fill that in up here. So f prime of x naught, still on the left side. And what will happen is this will go away, this will collapse to 1, this will go away, so I have f prime of x naught plus, I still have this term, but here the coefficients sum to 1. Here also they sum to 1. So now I have my 1 over h that's outside, and then I have times 1, because that's what the coefficients sum to, and then I have my third derivative term, which I'm just going to copy real quick. Okay. Plus my error. So everything reduced to this. Now let's simplify this a little bit. I have 1 over h times h cubed. That's going to collapse to an h squared. Okay. And then, well, the f primes on both sides, they'll cancel out. So So the error is equal to minus 1/6 h squared f triple prime x naught plus additional terms, like my dot 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 here, plus order of h cubed. And another way of writing this is we could just say this is the same as minus 1/6 h squared f triple prime at an unknown point c, and then nothing else. So we could express it that way. The main point is it's order h squared times third derivative over 6. So if we can bound that, that gives us an upper bound on the error. So what happened here was you decide which points you want to use in your approximation, or maybe the problem might specify it. Like in one of the explorations, I specify using x naught plus or minus h and plus or minus 2h. You fill in like this. You have a 1 over h, and then you have this expression here. Replace with Taylor expansions. And then because you want the first derivative term to survive, and you want as many other terms as possible to go away, and you're going to have, like, here I have 3 coefficients, so I can only impose 3 conditions. So in general, however many coefficients, that's how many conditions you can set. And then then you have your f prime, and then whatever is the first term that persists, that doesn't get canceled, in this case, this f triple prime term, that's where your error comes from. So really it's going to be minus that for the way I've written this. So you can follow this in deriving any numerical differentiation scheme, whether it's a first derivative or second derivative, and get your error term this way. So any questions about how this proceeded? Okay. Now, I may run out of time, but the other approach Lagrange interpolation. And what happens there is you specify that the derivative at x naught is equal to the derivative of an interpolating polynomial plus your error. And P2 interpolates f at the same points that I used before, x naught plus or minus h and x naught. So then what I do is use Lagrange form for P2. So that would equal f of x naught minus h times my Lagrange polynomial. Actually, going to use the index minus 1 again, like before, because it's x naught minus h. And then f of x naught times the Lagrange polynomial, and then f of x naught plus h times the Lagrange polynomial. And the idea is, I'm just going to, so what I would do is I would differentiate the polynomial and then plug in x naught. So the coefficients come from the values of my Lagrange polynomials, their derivatives, at x naught. But here's the problem, and you would see this, there's an example in the book where I work this out. These Lagrange polynomials, they're hideous, because they're using x naught plus or minus h, and the algebra is very messy. It's just ugh. So what I'm going to do is use simpler interpolation points, multiples of h, which in this case is minus 1, 0, and 1. So I make a change of variable. S is my new variable. It's x minus x naught divided by h. So the idea is if x is equal to x naught minus h, that gives me s is equal to minus 1. x equals x naught gives me s equals 0. And then finally, x equals x naught plus h, s equals 1. So in other words, I'm extracting from x whatever multiple of h it is away from x naught. So now what I do is I'm going to define tilde f of s to be equal to f of x, or really f of x of s. And then p2 of s equal to p2 of x of s. So I'm equating functions of x with functions of s, just so I can look at it from either point of view, where x of s is just reversing this change of variable. So it's x naught plus s times h. So here I've mapped from x values to s values. This just takes me the other way, just for convenience. So now what I can do is see how much I can fit this in 3 minutes. Okay. So now my derivative that I'm after is I'm going to work in S space. So it's derivative with respect to S of tilde f at S of x naught times ds dx. What rule is that from Calculus 1 that you learned? Someone said it. Chain rule. Here I'm differentiating with respect to x, but here I differentiate with respect to s. How are they related? By multiplying by ds dx. Notice the ds is cancelled. But when x is equal to x naught, s is 0. So I can fill that in here. So what I would do is I would substitute s equals 0 after I work all this out. But the thing is, what's the derivative of s with respect to x? Let's go ahead and differentiate this. What do you get? Keep in mind h is a constant. No. It's a multiplicative constant, not added. 1 over h. So, because this is a linear function. So derivative of x is 1, but you're multiplying by 1 over h. So what you get is, whoops. Dang it. So we get a 1 over h from this, and then we get tilde f prime at 0. So differentiating f tilde at 0 is the same as differentiating f at x naught, except for this factor of 1 over h that comes from a chain rule. And because I want to use a polynomial interpolant, that would be the same as 1 over h, my polynomial interpolant derivative at 0, plus some error. And if I represent this in Lagrange form, then I can figure out how to get this derivative expressed in terms of the values of f. So I have 1 over h. So I have tilde f at -1 Lagrange polynomial prime at 0 plus tilde f of 0 Lagrange polynomial 0 prime at 0 plus tilde f at 1 L1 prime at 0 plus error. Okay, unfortunately, I just realized I've gone past time, and this is not finished. So I will pick this up again. I'll post this anyway, but I'll resume this on Thursday. So be sure to send me any questions you have about the take-home. If you're considering doing that, if you haven't started, you really, really should. There are 5 problems, but they're not 5 easy problems. Okay.